In this video, we're going to take a look at how many of these first generation stars went supernova and created heavier elements up to uranium. As we've seen, these first stars have been fusing more and more iron in their cores. As the iron increases, the density increases, up to a point where the density becomes so much that the core collapses under its own weight, and the iron is broken up into helium nuclei, which are then broken up into protons and neutrons, and at that point, the electrons that are there are forced onto the protons, thereby making the protons neutrons, and you're left with an incredibly dense, in fact, with the density of the nucleus of an atom, so nuclear density, you're left with a ball of neutrons of nuclear density. This is also known as a neutron star, and the rest of the star is catching up. As the core rapidly collapsed into a neutron star, the rest of the star begins to collapse into this empty space. Now, the neutron star collapsed way too fast, so it couldn't keep up, but now, tumbling in from all directions is the plasma of the star. And once it crashes into this incredibly dense neutron star, it ricochets with a vengeance. It flies out, streaming out, with neutrons flying from the center through this plasma that is now escaping the gravitational pull of the host star. The star is throwing up, is shedding its outer layers into the surrounding interstellar region. But these neutrons that are flying from the center give the chance in these dying breaths of the star for the buildup of atoms up to uranium. You see, loose neutrons don't have any problem getting into nuclei. The reason we need such high temperatures for nuclear fusion is because we're forcing protons to latch on to other protons. And that's positive charge versus positive charge repel each other. So to force them together takes a lot of strength. But neutrons don't have any electrical charge. So when they're flying through, if they stumble upon the nucleus of an atom, they'll just land and nestle inside. There's nothing to stop them. And when you add neutrons to an element, what you often do is make the element unstable. And you make them unstable in a way that then has the neutron decay, giving off an electron and an anti-electron neutrino. Thereby, the neutron loses a negative charge, leaving it with a positive charge, leaving it as a proton, and suddenly we've now built up an atom from whatever it was to the next highest atom, the atom with one more proton. However, it's a little more complicated when it comes to the neutrons in a supernova because there are so many neutrons. So instead of adding a neutron and having that neutron decay, it's more like you could add 3 neutrons, or 5 neutrons, or 7 neutrons, and then have them decay. This is why this process is called the R process. The R for rapid because of the rapid addition of neutrons, as opposed to some other processes in nature which are slower with adding neutrons. But the main takeaway point is you can add neutrons, which then decay into protons, which brings the proton amount up in the atom, which builds the atom up until element 92, uranium. In the next video, we're going to look closer at all of these elements in the exploding envelopes of these supernova and see as the first minerals come into existence. If you found value in this video, like it, and if you're into big history, subscribe and stick around.